Okay, sure got the message by now. We're going to be looking at forces today. So the really big idea here that I want you to understand is that if we want to figure out how the motion of an object will change as time goes on, we really need to understand the forces acting on an object. So here we have an object on a ramp. Whoops, no, sorry, that's probably a little bit too soon for everyone. Here we have someone dropping a ball. So if we drop the ball, to understand how the motion of the ball will change as it falls, we need to understand the forces acting on the ball. Here we see an arrow being shot. If we want to understand the shape of the path that the arrow will follow, we must understand the forces acting on the arrow. Now, force is a vector quantity, which means it has a size and a direction. So all physicists love vectors. So that means when we draw forces, you'll see me drawing arrows. The length of the arrow indicates the size of the force, and the arrowhead indicates the direction that the force is acting in. Now, force is measured in newtons, so a small n for the unit, because the capital N is referring to the man, and we'll get back to him because physicists love the man. Okay, so in year 7, you might have described a force as a push or a pull, but we can do so much better than that. In fact, there are only 4 fundamental forces in nature. Well, if we do rewind close to the Big Bang, 2 of them actually merged and there were only 3. And people like Stephen Hawking, RIP, were trying to merge all of these forces into one fundamental force called the grand unification theory, but we're not there yet. So at the moment, there's 4 fundamental forces. The first one, gravity. Now, objects with mass, so a property that we give matter, mass, objects with mass attract each other. So the moon is attracted to the sun, and you are attracted to your cat because you both have mass. Now, gravity is a very, very important force on the scale of the universe. So what makes the Earth go around the sun go around the Milky Way center. Our galaxy sticks to its local cluster because of gravitational attraction. So on a large scale, gravity is ding, 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 the winner. However, on a much smaller scale, you don't see objects with mass moving towards each other. You don't see your pens creepily going across the table, being attracted to each other because they don't have mass. And that's because gravity is very, very weak. However, when you get a lot of it, because it's all attractive, it gets to dominate. The second fundamental force is the electromagnetic force. This one is combined. It actually produces 2 very different phenomena that you'd be familiar with. So an idea of charged particles, so protons repel each other. They experience a force of repulsion. So do electrons, but protons attract electrons. So this idea that we call charge helps us model these interactions that we observe. Also, with bar magnets that opposites attract and like repel. But these 2 phenomena that you might see in year 12 physics are actually related, and they're the one coming from the one idea. The 2 other forces are the weak force, and year 9 you should have done a little bit on nuclear decay, so that force is responsible for that process. And the strong nuclear force is responsible for holding a nucleus together, because we know in a nucleus there's positive charge really, really close together. Well, we know that they repel. There's something else going on there. It's called the strong force. Okay, so we'll do a little bit around gravity. We'll really get back to number 2 when we talk about chemistry. because this is the dominant force when we're talking about chemical reactions and bonds being made. But we can't work on these kind of scales because they're not very practical and they're very, very small. So we like to talk about other forces that occur, but they are just a consequence of primarily the electromagnetic force. Okay, so some other forces that are useful to think about might include friction or air resistance, a spring force, tension, or the normal force. Okay, so friction, we can think of here we have a sledder with a beanie, and this is snow. So we'll commonly refer to this as a low friction case. Okay, so the friction is coming from the interaction between two surfaces trying to move across each other. And when this occurs, often we lose lubricant in mechanical devices, so there's not too much wear on, say, two metal plates moving against each other. So really reducing friction in many circumstances is a very good idea. However, if you're braking in your car, friction is essential. Air resistance is another common force we might talk about. So here's me on my bicycle pushing through all this air. As I push on the air will push on me, and that's what makes it hard to ride very quickly. So that's why I've got a nice aerodynamic shaped helmet on. The spring force, here we have a Nerf gun copyrighted. So when you load your Nerf gun up, you compress a spring and then pull the trigger, the spring would release and apply a force to this non-lethal foam bullet. Another force, a tension force. So down here we have my attempt at drawing a person walking a dog. The dog saw a cat. A little bit awkward here that the lead is attached to the rear of the dog, but we'll run with it anyway. So here the tension force exists in the rope. So it's transferring a pull from the dog onto the dog walker. So tension also see in cables, in bridges, generally anywhere we see a string or a rope, we say it's under tension. The normal force, okay, so here we've got you sitting on your chair watching the video, having the time of your life. The normal force comes from another surface to surface interaction. So friction was when the two surfaces were moving over each other. The normal force is more when a surface is supporting another object. Okay, so what's happening here is the person is being pulled by gravity downwards into the chair. So if I represent that with a bit of an arrow, okay, so the person's being pulled by gravity downwards, but the chair has some strength. It can push back, okay, and it pushes back up on the person. Where this force comes from is from the compressibility or the compressible strength of the chair. So it's really hard to compress, and the chair will push back upwards, okay? Where this word normal comes from, it's not saying it's not strange or not weird. Normal means at right angles or perpendicular. So here, if we have a look at the surface of the chair in 3 dimensions, a normal force would be acting directly upwards at right angles to that surface. Okay. When we did have the ramp and we had a mass, you might have seen a lot of drawings with a force up like this. That's the surface normal force, so that's at right angles to the ramp. And that's because gravity is pulling on this mass downwards into the ramp, but the ramp has a compressible strength. It's going to push back up on the mass or the cart and apply a force normal to the ramp, at right angles to the ramp. There also would have been a little bit of friction in the scenario, and you might have seen a small arrow going against the motion as a frictional force. So all of these forces here look very different, but every single one comes back to one of the fundamental forces. Can you guess which one? I watched an interesting video on Veritasium recently, which said if you hug someone, are you actually touching them? And under the current circumstances, not advised, but essentially when you try and touch something, well, your finger, say, here's your finger, is made up of atoms, and we know that atoms have electrons whizzing around them. Well, all those electrons repel. So when you try and touch your pencil, say, well, the electrons here in the pencil are going to repel the electrons from your finger, and they don't want to ever touch. So there's no real contact between the finger and the pencil. The electrons aren't touching each other. They're not like two balls that will sit next to each other when your finger's here and the pencil's there. There's actually always a distance between two objects. So this idea of touching, there being perhaps a contact force, is really just what helps us think about what's going on. Because what's really going on is pretty weird. Okay, moving on. There are forces acting on you all the time. Okay, so you're sitting on your chair, you're in the classroom, you're outside having some exercise. The earth is always pulling down on you due to gravity. So the gravitational attraction of the earth on you is always present. It doesn't matter if you're an astronaut going around the earth, that force is still there. You're still being attracted to the earth. You're still being attracted gravitationally to the sun. You can't escape gravity. Also, you might notice there are air molecules hitting your face all the time, applying a force to you. So you can't escape forces. But if we want to consider how we're going to move, one force alone doesn't tell us the story. One force never causes an object to move. We've got to consider the sum of all forces. So this is really important because it's a common misconception that if we have a table and say a cup sitting on the table, we observe that the cup is not moving. So a lot of people make the assumption that there's no forces acting on the cup. But that's not true. There's always gravity forcing. It's just that the forces are balanced. But this is tricky. We need a little bit of help. Okay, so it's Sir Isaac Newton we need help from. So this guy invented calculus because he just wanted to. He developed that because someone actually asked him about Halley's Comet, and they weren't sure how to describe the path it takes around the sun. So he invented a brand new branch of mathematics just to solve the question. And he also wrote one of the foundational, biggest, most important books of human history called In Principia, that clearly demonstrated or showed us how objects move and really laid the groundwork for modern physics. So Sir Isaac Newton, he'd be really pleased with this shout out. We're going to get your help to get some more ideas about force. So Newton came up with 3 laws of motion. The first law of motion says that if the forces acting on an object are balanced, then the velocity of the object will not change. And if the velocity is not changing, that means we have constant speed in a straight line. The direction is being the same. So balance forces in a couple of different scenarios. Again, back to the classic mug on the table. Well, then the forces acting here, I draw arrows to represent them. The mug, because it has mass, would have the force due to gravity acting down on it, so a downwards pull. but it also has the normal force from the table pushing up. And those forces are balanced because the velocity of the mug isn't changing. Okay, because it's not moving, we observe that. So from that observation of constant velocity, we know the forces acting on the mug must be balanced. So here I've labelled the normal force as Fn. It's pushing up from the centre of mass of the mug, whereas gravity, Fg, is pulling down on the mug. So I always show my force vectors coming away from an object, never a push in. Another little bit of notation here, I've put a couple of dashes on these vectors because they have exactly the same size. So to show that, that's the notation that I use. We could also observe a car travelling down the road at constant velocity. So again, that means we must have balanced forces. So let's just draw a simple diagram of the forces acting on the car. We would have, again, the force due to gravity acting on the car because the car has mass. The road would be pushing upwards on the car, and we'd call that a normal force. And they must be equal in magnitude. But because the car is moving, it'll also have some air resistance against the direction of travel. So I could label that F air. So to balance the forces, I think we see quite clearly that vertically we have the forces balanced. However, you should know from driving in a car, if you want to maintain your velocity or your speed on a flat road, you need to press down the accelerator. You need a thrust force from the car. So there must be another force acting on the car coming from the tyres on the road. We'll call it a thrust force coming from the motor. And these two forces here as well must be equal. So what we see here in my diagram are balanced forces. They're cancelling each other out. Down here we have a bull, and here I'm pictured as a cowboy, and I'm swinging a lasso around. And I could be doing that at constant speed. We could see the lasso going around a circle at a constant speed. However, the direction is changing. So this is a situation that sometimes catches people out where the forces on the lasso are not balanced. Okay, so to have the condition of balanced forces, the object must have a constant speed, could be stationary, but it must be travelling in the one direction. The second of Newton's 3 laws of motion talks about what happens if the forces are unbalanced. Okay, so they're not cancelling each other out. So a couple of scenarios here of unbalanced forces. Here we have a skydiver who just jumped out of a plane. They haven't been travelling too long. So here, again, because the skydiver has mass, they'd have a weight force. Sorry, I haven't called it that yet. The gravitational force acting down on them. I'll come back to weight force later. And they also have some air resistance. I could call it F air. But it would be the case if they're accelerating downwards, if they're getting faster, these forces wouldn't be balanced. We'd see the gravitational force would be bigger in size than the air resistance force. This diagram looked good at the time. It's a tug of war where these people are in the motion of falling over. So they're accelerating. So even though there might still be a pull in this direction, a greater pull in one direction, this was a bit of a, we'll let that one go. So if the forces are not balanced, well then the object will accelerate. What Newton's second law was really about was the relationship between the net force. So the net force is the sum of all the forces. Okay, because some forces might be in the same direction, adding up. Others might cancel out slightly and reduce the size of the net force. But when we add up all the forces, we get the net force. And that net force is related to mass and acceleration. So we see from this equation that if we consider a constant mass, then if we double the force that we apply, we'll double the acceleration. So I could say here there's a direct relationship between force and acceleration. The equation also tells us if we have a small mass versus a large mass and we apply the same sized force to them, well then the larger mass will accelerate at a much less rate. Much slower rate? No, that sounds better. The acceleration will be less. There we go. I won. Okay, but the smaller mass will experience a greater acceleration. So one useful way to think about mass, and mass is a really, really complicated idea, is that an object's mass is a measure of how much it resists a change in motion. So sometimes it's referred to as an inertial mass. Okay, so you might hear that objects are lazy, they want to stay where they are. A rock on the ground doesn't want to move. An object flying through the sky doesn't want to move. And the more mass it has, the more inertia it has. And that means it's got a greater tendency to keep on doing what it's doing. Or another way of thinking about it, something with a large mass, you need a large force to change its motion. Okay, so mass can be thought of as the relationship between the force applied and the acceleration you observe. Another way to think about mass is how much matter an object is made from. Beyond that, perhaps in year 12, I might mention that mass actually has a lot to do with trapped energy, and E equals mc squared, mass and energy really are the same thing, but I don't want to blow your minds too early on in year 10. You might not survive. Well done in getting all the way to the end of the video. There's some really big ideas there, really important stuff that we will investigate more, both on style and perhaps another video lesson, depending on time. It takes a while to make these. I'm going to assume that no one is actually watching now, so as a bit of an Easter egg, here's a photo of my cat.